Hello, and welcome to this series of lessons on geometry. My name is Johnny Dlabu. In this series, we will work with theorems and exercises, or riders, that form part of a field of maths commonly known as Euclidean geometry. To start, we will look at similar polygons. We are going to focus on the properties of triangles. First, we'll establish the conditions for shapes to be similar and their sides in proportion. Then we'll go on to prove several theorems about similar triangles. Then we will use these theorems to solve exam-type questions about triangles. The later lessons in the series deal with the Euclidean geometry of circles and ways to work out riders. During these lessons, you should see that there are better ways of learning theorems than just remembering them off by heart. Your memory is likely to let you down if you try to remember things that don't make sense to you. But if you work with the logic in the theorems, you can support your memory with your knowledge and your common sense. By the end of this lesson, you should be able to define and use the conditions for polygons to be similar and proportional. We've asked one of our learners, Kanya, to help us with these lessons. She has been waiting patiently at home for us to get started. Let's cross over to her. Hi, Kanya.
Hello, Johnny.
Are you ready to do some geometry?
Absolutely. Where do we start?
That's the spirit, Kanya. We are going to begin by going over some terminology. First, let me remind you that a polygon is just a closed shape with straight sides. So a triangle, a rectangle, and a 10-sided shape are all polygons. You have probably come across the terms similar and congruent before, but let me remind you again. In previous grades, you worked quite often with congruent triangles such as triangle XYZ and triangle KLM here. Congruent triangles provide useful tools for proving riders, but more about that later. Any two shapes or polygons are congruent if they are exactly the same size and shape. This means that all their corresponding angles and side lengths are exactly the same. Do you think you've got that?
Yes, I think so.
Are you ready to look at an example?
Yes, Johnny, I'm ready.
Here are two congruent quadrilaterals. This means that their corresponding angles and lines are equal. Kanya, do you think you could tell which are the equal angles just by looking at these?
I'm not really sure.
All right, let me see if I can help you a bit here. I am going to move the second quadrilateral so that it sits on top of the first one. This should give you a better idea of which angle in the first quadrilateral corresponds to which angle in the second quadrilateral.
I think I see it now. It looks like angle A equals angle F, angle B equals angle G, angle C equals angle H, and angle D equals angle E.
Let's check that quickly. Well done, Kanya. So even though the orientation of the two shapes is not the same, they are identical in every other way. And so we say that they are congruent. And this means that AB equals to FG, BC equals to GH, CD equals to HE, DA equals to EF.
May I ask something?
Of course, Kanya.
I was just wondering, is there some special way that we write that mathematically?
Yes, there is, Kanya. I was just coming to that. In maths, when we want to say that the shapes are congruent, we use this symbol. We also need to take care with how we name the shapes when we make a congruency statement. We need to refer to the congruent figures in the same order as the angles and sides that pair up in its shape. In our example, angle A corresponds with angle F. Angle B corresponds to angle G. Angle C corresponds to angle H. And angle D corresponds to angle E. So our congruency statement says that polygon ABCD is congruent to FGHE.
So does this mean if we see a congruency statement, we can see at a glance which sides and angles are equal in shapes?
Quite right. That's good thinking, Kanya. Now that we have looked at congruency, I would like us to spend some time looking at similarity. Can you remember what similar polygons are?
Not really.
Two shapes are similar if their angles are the same size and their sides are in proportion. To put this more accurately, two shapes are similar if their corresponding angles are equal or congruent, and their corresponding sides are in proportion, but not necessarily equal to each other.
Let me see if I've got this. The difference between congruency and similarity is that congruent shapes are identical in shape and size. Similar shapes have the same shape but differ in size.
That's correct. Here, let me illustrate this with an example. Here are two irregular pentagons that are similar. In this example, angle A equals to P. Angle B equals to Q. Angle C equals to R. Angle D equals to S. Angle E equals to T. I'm going to put one on top of the other like we did in our previous example.
Oh, I see. The shapes are the same, except that one is smaller than the other.
Exactly. And although the corresponding sides are not identical in length, they are proportional to one another. Or you could say that they are in proportion. This means that the ratios between their lengths are equal. In other words, the ratio of AB to PQ is the same as the ratio of BC to QR. This is true for all the corresponding sides of the two polygons. If we wanted to write this mathematically, we could show the ratios as fractions. So AB divided by PQ equals BC divided by QR. These in turn are equal to CD divided by SR and equal to ED divided by TS. And these are also equal to AE divided by PT.
So in this example, the corresponding angles are equal and the corresponding sides are in proportion. So we can say that the shapes are similar.
That's right, Kanya. The requirements of similarity are met. This is the symbol we use to indicate similarity. It's important to note here that, as with congruent shapes, we need to name the shapes according to their corresponding sides and angles. So in our example, we can say that ABCDE is similar to PQRST. Are you with me so far, Kanya?
I think so. I understand what makes shapes similar, but I'm not quite sure about this in proportion thing. I can't see how the ratios can be equal.
All right, let me show you using lines only. Here are two line segments. These line segments are divided in proportion to one another, much like proportional sides in similar shapes. When two line segments are divided proportionally, the ratios between their divided parts are equal. For example, if the ratio of AB to BC is the same as the ratio of DE to EF, then AB divided by BC must equal DE divided by EF. This will be true no matter how long or short the two lines are. Now, let's prove that this is true using the numerical values. For example, AB divided by BC is equal to 16 divided by 12, which if we simplify is equal to 4 divided by 3. DE divided by EF equals 8 divided by 6, which is also 4 divided by 3, which means that AC and DF are both divided in the ratio 4 to 3. So we can say that the line segments are proportional or in proportion.
I think I get it now.
Excellent, Kanya. Now, do you think you could name some other ratios that are equal on these two line segments?
Wouldn't AC divided by AB be equal to DF divided by DE? Because that's 28 divided by 16, which simplifies to 14 divided by 8 for AC divided by AB. And DF divided by DE is 14 divided by 8 as well.
That's excellent, Kanya. And there are some other statements we can also make if the two line segments are proportional. For example, from the first ratio, if we cross multiply, we get AB times EF equals BC times DE. If each fraction is inverted, we can also see that BC divided by AC equals EF divided by DF. The full length AC divided by BC equals the full length DF divided by EF. These ratios are also equal. Now we are ready to use the properties of similar polygons. Here is a question we can solve. See what you make of this, Kanya. Polygons PQTU and PRSU are similar. Calculate the value of x.
I'm not quite sure I know where to start.
Well, we are already given that polygons are similar. So that means that the corresponding sides are in proportion. Can you identify which sides corresponds?
Well, I can see that PQ from the green polygon corresponds to PR in the blue polygon, and TU corresponds to SU.
That's right. We are aiming to find the value of x, which is the length of side PQ, so we can write down an equation using proportional sides. Can you find two equal ratios that include the side PQ? Here is a hint. It makes the maths easier if you start with the unknown side that you are looking for in the numerator, not in the denominator.
I'm a little confused.
Here is one possible statement that will help us. PQ divided by PR is equal to TU divided by SU. Put in all the values you know for these lengths and see if you can calculate x.
I see. PQ is x and PR is x plus 3 minus x. TU is 3 and SU is 4. We can simplify this denominator. X minus x is 0, so we are left with 3.
Correct. Now, using cross-multiplying, we get 4x equals 9, and so x is 2,25. Well done. I think that's all we have time for today.
Thank goodness. I don't think I could fit any more knowledge into my brain today.
I'm not so sure about that. What concerns me is making sure that you remember what you learned today. So here's a task to consolidate today's lesson. Now, you should be ready to tackle a question about similar shapes. Triangle BCD is similar to triangle RBQ. RBD and QBC are straight lines. Question 1. Determine the ratio of RB to BD. Question 2. Determine the length of BQ, QC, and CD. In this lesson, we have worked with similarity and proportion. Now we are ready to prove the theorems using this knowledge. Until next time. Please check our website to get the information needed for the task and other print-related information.